should say, record this. Yeah. So the solution here is a point of intersection. We're just looking at linear system. Just a little preview because I like it so much. In college algebra, you will look at nonlinear systems. For example, a circle could be matched up with a parabola, like so. And now, if your solution is the point of intersection, now you have to find how many? 1, 2, 3, and 4. 4 points where they intersect. And sometimes that has to be done through quadratic formula and some other stuff. But we're not doing that. We're just looking at a linear equation where if there is a solution, not always a solution there. If there is a solution, then we have to find that point of intersection. And the methods for solving is graphing, and that's in section 3.1. Then we look at substitution method. Now we're going to do it algebraically, which is in 3.2. An addition method, which sometimes is also called elimination method, is in section 3.3. And most of the times, well, unless I tell you, we use these two. Now on the test, I can tell you already there will be some questions where you choose the method of your choice. If there's a method you like better than the other, then use that one. Unless I specifically tell you do substitution method, like in 3.2. When I grew up, it's vaguely I can remember, but when I was in school, we mostly did elimination method. And that's my preferred method of choice. Don't ask me why, but that I use that more than the other. But there are certain ways you can see which method you should use. That makes it easier on you. Sometimes addition method is not always the easier one. For me, it just seems quicker. Okay, so these are your methods. But before we actually go, there's always a couple problems in the book where they give you a system of equations. So here you have two equations, 3x plus 2y equals -8. And y equals 2x minus 18. And the question is, determine if this ordered pair is a solution to this system of linear equations. So what you have to do is you have to plug them in. -2 is your x coordinate and -1 is your y coordinate. And it has to hold true for both of them. It cannot just plug it in the first one, say, oh, the first one works, so yes. No, they have to be true for both of the equations. And the answer is either a yes or a no. So let's look at the first one. We have 3 times what? -2 plus 2. 2 times what? -1. Is that -8? I always put a little question mark here. Is that -8? Yes or no? Do the arithmetic. Yes. What's 3 times -2? -6 plus -2. That indeed is -8. So we got to check on the first one. Don't forget, it has to check in both of them. So the second equation is y equals 2x minus 18. What we're plugging in for y? -1. Is -1 equal to, question mark, 2 times what? Why am I screaming? I feel like I'm screaming. 2 times -2 minus 18. I don't even have to do the arithmetic to see that that's not happening. -4 minus 18 is not equal, that's a symbol for not equal to -1. So what's the answer to this question? Is -2, -1 a solution to my ordered pair? No. No, thank you. No. Okay. Now let's try the point for -10. Again, we're plugging it still into the same system here. Now this time we have x is 4 and y is -10. 3 times 4, I'm trying to use different colors, but it's 3 times 4 plus 2 times what? -10. Is that -8? Three times 4 is 12.
Yes.
Plus a -20. Is that -8? -8 equals -8, so we got a check mark here. Now let's try the second one. Y, we're replacing y with what? -10 equals 2 times 4. I'm trying to use different color. That's really 4 minus 18. So let's do the arithmetic. 2 times 4 is 8. 8 minus 18, what is that? -10 equals -10. Check mark here. So what's the answer to this question? Yes. So all you have to do is plug them in. You don't have to solve. You don't have to do anything but plug them in and see which one works and which one doesn't. They have to work for both of the equations. As we could see with this one, the first one did work, but the second one did not. Everybody good? Yeah. Okay, now we got to look at our solutions. I said we have a solution that is x and y, the ordered pair. But that doesn't always hold true. There's actually three different solutions, 3 different cases. Let me do 3 coordinate systems. Chirp, 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 chirp. Okay, the first one is we have a problem. Now I'm just randomly making these graphs up. We have a system of equations, and the first graph looks like so, and the second graph looks like so, and we can clearly see that those 2 lines intersect. So we do have one solution here. And the points intersect. That's how this is in geometry, geometrical terminology. That's not even a word, I just made it up. Maybe it is. So we have 1 point. Okay, so that's one case. Case 1. We do have a solution. Now when we do have graphs and they look different, they are categorized as, in different words, you got to remember that, as consistent, independent, and in terms of solution, they have one solution. So my 3 cases are put into different groups, different categories. If you do have a solution, be it one solution or all of them, then the system is to be said consistent. If one graph has nothing to do with the other one, then they're independent, and we have one solution here. How do I remember that? I call it CIO. I remember things just by abbreviations and alphabet. CIO. And I'm going to ask you throughout the entire morning, what does CIO stand for?
What was the independent one again?
The independent means one line has nothing to do with the other. CIO. Not CIA, but CIO. Okay, so that's one case. This is our preferred case because, oh, look, they are intersecting. Beautiful. And we can actually check and plug in this ordered pair into our system and see if that's actually the case. Now, one reason why mathematicians don't prefer the graphing method is because it's not very accurate. Some of us have rulers, some of us don't, some of us make thick lines, some of us make thin lines, some of us make big red points here, and others do not. So it's not a very accurate way of actually finding a solution. That's why the graphing is not the preferred method. Algebraic way is the preferred method. Okay, case 1. Case 2 is you graph your lines. I give them to you. And one graph looks like so. And the other one looks like that. What do we know about those lines? They are parallel. We have parallel lines here. What do you think about a solution if you have parallel lines? Do they intersect? No. So that means there is indeed no solution. So you could have a case where you have no solutions. Now the categories are, if you have no solution, then it's inconsistent. It's still independent because one graph had nothing to do with the other. And there is no solution. So on a test, you actually have to write down no solution. You also may have to write down that it's an IINS. IINS stands for independent, inconsistent, no solution. And you can just write down IINS because I know what it means. And hopefully you too. What is CIO again?
Consistent, independent, one solution.
Okay. Okay, and the last case is the case where you have two equations. They may look totally different, but through reducing and whatnot, they are exactly the same. So I'm only actually going to graph one line. They are exactly the same line, and that's called coinciding lines. The lines coincide, means they are the same. Now, when the lines coincide, they are consistent. Now, maybe I should ask you, when the lines coincide, what do you think we know about the solution?
There's like infinite.
You got the book open?
Oh yeah, but I'm looking at my notes.
Okay. So when the lines coincide and the other line, let me draw a line that has a different color, but it's exactly on top of the purple line. That means they intersect everywhere. So there are infinitely many solutions. You actually have the three cases on page 195. So if you have one solution or many solutions, the system is consistent. Consistent means you have solutions going on. Now that case is the only case that is dependent, because one line is exactly the same as the other. And since I can't spell infinitely, I always forget an E in there somewhere, I say many solutions for a reason. So we have infinitely many solutions, but, oh, you can't see that. The many is right here. Many solutions. There you go. Many solutions. Now, how do I remember that? CDM. And over the years, students told me that stands for can do math. At first we said can't do the math, but that was too negative. So we switched to we can do the math, right? So CDM stands for can do the math, and that means we have infinitely many solutions. And I can write it out once in, that's an N. I always forget that E in the middle. So here you go. Infinitely many solutions. Okay. What is IINS? Not looking at your notes. What is can do math? What? What's CIA? No, CIO? What's IINS? I forgot. Okay, if you see a system that looks like that, what kind of system do you have? CIO. If you have a system that looks like so, what kind of system is that? CDM. What is CDM again? Without looking? What kind of system is that? What do we know about the lines? Okay, I'm going to ask you again in 10 minutes. So, there are some problems in the book on page 200. I guess I took some pictures of it. The first one, what kind of problem is that? What kind of case do we have here? CIO. The second one. CIO. Number 11. What is the instructions anyway? Maybe you should look at it. Identify whether the system is consistent, inconsistent. Identify whether it is dependent or independent. And identify the number of solutions. So by telling me these abbreviations, that's all you really need to say, because I know what that means, and maybe, hopefully you do too. What's CIO again? What's can do math? Okay. And they have the systems, they graph them already, so, and you see the cases, you graph your, oh, let's practice that too. Again, this is the hard part, I guess, where it gets a little tricky is what is that point of solution? These two, 9 and 10, are CIOs. So if we look at this in the book or here, what would be the solution? We know there's one solution. What is it? -1, 2. You actually have to write down that ordered pair. So if you look at number 10, what is the solution? Oh, 3, 3. I can't make it larger, but you should have a book in front of you. Yes.
Is it possible to have more than one solution then?
No. Not for linear. Now remember the one I showed you, the nonlinear at some point. Here you go. Here it's possible to have more than one solution. But with the linear one, how would I graph that? I wouldn't. It wouldn't be a straight line. I can't intersect again, or unless I go this way and then go here. Then it's not a linear anymore. So, no. But good question. Okay, I think there's some more. Number 12, what do we have here? What kind of system is this? IINS. Number 13. Here you go, it just did homework. I got a sneeze, maybe not. Well, maybe I do, thank you. Okay, next. Now we're actually going to graph one. Number 15 says solve the system by graphing. For systems that do not have one unique solution, one solution is also in math considered to be unique. Also state the number of solution, whether the system is CIO, IINS, and can do math. Of course, that's not what it says here in the book, but not so much. Okay, so 15, you have the two equations. How do you want to graph this? We learned how to graph linear equations in chapter 2. So if you look at, we have to graph each of these equations independently. So 2x plus y equals -3. How do you want to graph this?
First we could put it in, let's look at our form.
Put it in y equals mx plus b form, and then you just find then you find the slope and the y-intercept. So how do I solve 2x plus y equals -3 for y? What do I need to do?
Just move the x to the other side.
How?
By subtracting the x.
I subtract the x?
So
Well, you said x, you gotta say 2x, right? Yeah. By subtracting the 2x, and you get y equals -2x minus 3. So what's the slope here? And what's the y-intercept? Okay, let me graph this first. 0, -3 is right here. And then the slope is -2. And that was another thing on the test. You had to graph something and the slope was negative, or you had to figure out if that was a negative. I can't remember the actual problem. But m here is -2/1. But some of you made both of them negative, and now that makes it a positive. So if you graph this with rise over run, only one of them can be negative, not both. And I always, at least for my own graphing rule, I always make the top one negative. So I either go down 2 or go up 2. In this one case, I'm going to go down 2 units. And then my run is positive. I'm running in the positive direction, 1 unit. And my second point is right here. Now, if you're going up 2 units, then you have to make the 1 negative. And then running in the negative direction, and you have a third point here. But my rule of thumb is always to make the top number going up or down if it's negative, and the bottom one is positive. So now we're going to connect the dots, but I don't want to make them so thick because then it's not all that accurate. 1, 2, 3. 1, 2, 3 over 1. See, I'm already missing my target here. This looks like I don't like that at all. Well, that's what I did wrong here. I went up 3, it's only 2. Slope is 2 over 1, so here we go. Up 2 over 1. There's our first line. Okay, now we got to deal with negative x plus y equals 3. And if we do this the same way, we're solving for y. What do we have to do first?
Move the x to the opposite side.
Move the x. In this case, it's 1x. So y equals x plus 3. What is the slope? 1. And the y-intercept is 3. You can already see from comparing the slopes. What do we know from chapter 2? If the slopes are the same, the lines would be parallel. So these lines are not parallel. If they are opposite reciprocal, they would intersect at some point in time. Perpendicular. Let's see what's going on here. We have a 0, 3 y-intercept, and we have a slope of 1 over 1. So 1 over 1. I just made more points so I can show it better. Here you go. Beautiful. Now we can see that they are intersecting. What is the point of intersection here? Negative 2, 1. Yep. And what kind of system do we have here? Quickly you forget. Yeah. CIO. This would be a CIO. What's IINS?
Independent, inconsistent.
Without looking down, what's can do math?
Consistent, doing.
Dependent.
Consistently doing.
Yeah. We're doing the math. Yes. What's CIO? I'm going to ask you again. How about, oh, beautiful. Beautiful 20. Beautiful 20 is in function notation form, but what does f of x, what does it really stand for? Y. So we don't have to make any changes here. We have y equals 1/2 x plus 2, and we have y equals 5/2 minus 2. We can see the slopes are not the same, so those lines are not parallel. Somehow they're going to intersect. What's the slope of the first line? 1/2 with a y-intercept of 0, 2. What's the slope of the second line? 5 over 2 with a slope with a y-intercept 0, negative 2. There you go. Let's do it. 0, 2 is right here. And they're both positive, right? I'm going to go up 1 and over 2. There's my next point. Up 1 over 2. I'm going to go up 1 over 2 to make a third point. And then I'm going to go down and negative to make a fourth point, just to get a good... You don't have to do that. You can make 2 points, and then you can connect the dots. There you go. Blue it is. We have 0, negative 2. And then we're going to go up 5. 1, 2, 3, 4, 5, and over 2. Oh, that's beautiful. We can already see what's going on here. Connect the dots. Now, when you're graphing, you got to make a graph. You can't just plot points. Just like in the coloring book. I grew up with a lot of coloring books because they were cheap. And the coloring books, my favorite part was when you have to connect the numbers and see what it is. Yeah, that was always so exciting. And same here. So we had to draw lines to make this a nice, usually it was some kind of animal or something. Yeah, coloring books. Do they still have them? Good. But now they have the coloring book for adults, you know. Those, I don't know. I bought one once and I gave up. I don't like them. So what kind of system is number 20? What does that mean? And what is this one solution here? 2, 3. Right. Okay, what time do we have? I think, well, let's do number 22. Why not? That 22 in the book. Yeah, it's exactly this problem. There you go. 1, 2, 3, 4, 5. -3, -4. 1, 2, 3. Here you go. X. Okay. Let's do the second graph first because we know what kind of graph that is. What kind of graph is that?
Horizontal line.
That would be a horizontal line at -3. So that means there got to be a point of intersection here because y is -3. We already know that. How about 3x plus 2y equals 6? Solve this one for y. How? Subtract 3x. 2y equals -3x plus 6, and then divide by 2. Y equals -3/2 x plus 3. That means the slope is -3/2 with a y-intercept of 0, 3. Okay, let's see what's going on here. 0, 3 is right there. -3/2. 1, 2, 3 down and over 2. 1, 2, 3 down and shouldn't do that. And over 2. You can see without any lines, without anything, without any coordinate system here with nice little square boxes from the book, you see how this cannot be very pretty here. But it's an estimate. You got to be careful. I don't have a ruler here, so this line, here you go. What kind of system is this? CIO. And what is the solution? 4, -3. This point right here. I'm trying to be as accurate as I can. Y equals -3. Obviously, we have the second equation is satisfied. If we plug in the point in the first one, 3 times 4 is 12. 12 minus 6 indeed is 6. So we have the correct point. Okay, what else do we have? 29. Let's see. Let's do one more. Okay, you guys do 29. I'm done. Why am I always talking? 29, graph it. Tell me what's happening here. If we divide by 6, the second one, we get y equals 1/3 x plus 2. M is 1/3 and 0, 2. Okay, I do this one because that one was not much work. You do the one with more work. And I graphed the green one. Slope is 1/3. Okay, what about the first one? Let's make it purple. How do you solve this one for y? Right. So that would be 1/3 x plus 2. Oh, look at that. The purple and the green. They didn't look the same in the beginning, but now once we solved them for y, they are the same. So what kind of system do we have here? We can do the math. That means infinitely many solutions. I always explain it like so. Maybe I shouldn't. When they intersect, they shake hands, they get to know each other, they shake hands. When they're parallel, they decided they didn't like each other. And when we can't do the math, they decide they like each other too much. So here you go. There you have it. Those are your 3 choices. A little true or false. Oh. A little true or false. I like those problems. 33. A consistent system is a system that always has a unique or one solution. A consistent system is a system that always has one solution. True or false? That would be false. Why is it false?
Because you have the coinciding lines. And
Right. You can have infinitely many solutions. If 2 lines coincide, the equations are dependent. True or false? True, false, what?
false.
If 2 lines coincide, the equations are dependent. Coinciding lines, what does that mean again? I forgot.
Are they crossing?
Coinciding lines are number 29 are coinciding lines, right? So are they dependent? Yes, they are. CDM. 34 says dependent equations form a system that has no solution. False. And 36, if 2 lines are parallel, the equations are independent. INS. Number 38, I've seen on tests before. Let me get a new, my favorite problem. 38 said what? X, we had -2, 6. That is the solution. -2, 6. You come up with a system of equation that has that solution. Yeah, we're practicing our thinking.
Are we writing this in like the y equals mx plus b format?
Well, you got to come up with a system of equations. Yes, it could be in that form. Yeah. So where you have 2 equations here that have this solution. Oh, which reminds me, remember I wanted to tell you I was going to have you test the Nearpod out at home and see if that works? Oh, I can give you a problem like this. Yeah. 4 bonus points on the next test. Any thoughts? Anybody? This is actually a really, once I tell you, simple answer. Okay, Gabriel, let's hear it.
I don't know, this might be totally wrong.
Well, that's why we'll want to know if it's... Okay, go for it.
So, I just gave myself a random slope, so it's like m equals 3.
3, and then using that one equation, I just did y minus 6 equals 3 parentheses x plus 2.
Okay.
And then after solving that, I got y equals 3x plus 12. And I just set it what would be perpendicular. So y equals negative 1, 3x plus 4. And then hopefully they should intersect at that point.
Plus 4?
I don't know, I just did another random slope.
Okay, let's see. If 6 equals negative 1/3 times a negative 2 plus 4, I can tell you that's not 6 because of the 1/3. But if you just make that an x, no, yes. If you make this a negative x, and then you plug in a negative 2, that would give you a positive 6. And let's see if the top one works. 3 times negative 2 is negative 6 plus, oh, here you go, we got one. Y equals 3x plus 12, and y equals negative x plus 4. They both work, right? Negative 2, 6. So 6 equals negative 6 plus 12, yes. And 6 equals negative 2 plus, yeah. Oh, yeah.
Wait, I was right?
Well, the 1/3 I didn't like, and I made that an x, a 1. Got rid of the denominator here, and then it worked. Yeah.
Yeah.
Yeah, there you go.
On the bottom, so I don't really know what's going on, but
Well, I made it work. You got me started, and I made it work. So, yeah,
okay.
yeah. Thumbs up. You want to see my solution to this problem?
Yeah.
No, but I'll give it to you anyway.
Is that,
Exactly what I did.
oh, can you do that on the phone?
Yeah,
Oh.
that's a system of equations.
Oh my gosh.
That was pretty good.
Yeah. But yours was much more thinking involved. So that's actually better than mine. I didn't think about that at all. But if you graph it, x equals negative 2, that's a vertical line, right? And y equals 6 is right here. That's a horizontal line. So where do they intersect? Right here at negative 2, 6. Yep. That would be the easy. That is a system of linear equations. X equals negative 2 and y equals 6. That was my solution. But I honestly like your solution better, Gabriel. So that's good. Cool. Okay, so... Anybody else had something that worked? I mean, that's the way you approached this was a good
Can you
start.
look at either 39 or 40, just to kind of clarify?
39 or 40. What is CIO again?
Consistent independent one solution.
Oh, now you. Okay. Well, yeah, I don't want to start. So let's look at 40. I don't want to start 3.2. We do that on Friday with 3.3. 3x plus my equals negative 22. Nx plus 4y equals 6. Find m and m such that the solution is 2, negative 4. That is our solution. Now that's kind of an easier problem because you plug in. Let's plug this into the first one. You get 3 times 2 plus m times negative 4 is negative 22. 6 minus 4m is negative 22. Subtract 6. Get negative 4m equals what? Negative 28. And then divide by negative 4. That makes m to be 7. So here we had a lot already that was given to us. We just need to plug them in.
Okay.
So m is 7, and let's find n. Why not? 2 times n plus 4 times negative 4 is a negative 16 equals 6. So add 16. 2n equals what? 22. Divide by 2. N is 11. So our system of equations in this case is 3x plus 7y equals negative 22, and 11x plus 4y equals 6. Is that true? 22 minus 16. Yep, there you go. So, right, Ashley? Plug it in. 6. No, something's wrong. What's wrong? 6, no, nothing's wrong. 3 times 2 is 6, minus 7 times 4 is 28. 6 minus 28 is a negative 22. 11 times 2 is 22. 22 minus 16 is hopefully 6. So, good work.
Thank you for going over that.
Yeah, yeah. Okay, that we're definitely done with 3.1. So on Friday we're going to do both methods 3.2 and 3.3. Any questions?